Welcome you all to the next lecture on Inorganic Chemistry of Life, Principles and Perspectives. What have we done in the recent classes? In the recent classes we have looked at the aspects relevant to biology of those of the alkali and alkyl earth elements, that is sodium, potassium, calcium and magnesium. Now we will transit into the transition metal biological chemistry. So therefore, let us first look at the periodic table which is relevant to the biological systems, and these are the ones where you have a catalytic activities, particularly we have looked at sodium, potassium, magnesium, calcium. The next comes is the transition metal series, the titanium till zinc. Though the titanium is sort of as a micro nutrient element is understood, but there is no enzyme yet been identified. Therefore, we will not take up this case of the titanium. We will look at vanadium, and chromium is also not involved in any enzyme. So, we will be leaving out. Then manganese, iron, cobalt, nickel, copper, zinc. So, we will go in this particular order of the transition metal series to look at the enzymes. I would be spending a lot of time in iron enzymes because we have both the heme based and non-heme based. Then we will spend a lot of time on copper and zinc as well, maybe some extent to molybdenum. In other cases, we will be spending only a limited number of examples of each of these. Okay, so let us start with the biological inorganic chemistry of vanadium. Vanadium, as you know, as an element, as a chemical element, can show a variety of oxidation states. Anybody has a guess what kind of oxidation states? Yeah, think a moment. It can show from +5 to -1. Okay. So, it can show a large number of oxidation states, but all of these oxidation states are not well favored. Some of them are more frequently found than the others. And in the biological system also, we should always keep in mind the kind of oxidation states that are favored are most common oxidation states. And if you look at the most common oxidation states in the vanadium are the +5, +4 and +3. We will see the reasons why +2 and all are not so common just in a while. Okay. So, before we go to that, let us look at this particular slide where some enzymes are shown and the corresponding oxidation state. Haloperoxidase, and these are some information which you can read any time, like the source, system, the function. The function is it halogenates the organic substrates, and the oxidation state in this is the +5. Okay, and the next one you see that it is the nitrogenase. In the nitrogenase you have nitrogen fixation, and the main oxidation state in this is +3. Then ATPases etc. it stores, and there is something called amavadin which is a storing kind of a protein, not so much details are known, as a +4, and there is vanadobin. Its biological cells, it can be +5, +4, in a few cases even +3. A lot of therapeutic compounds are also +5 and +4, and some of their activity is in the insulin based activity. So, what do we understand out of this particular slide or table is that the vanadium is involved in the biological systems in a, of course, limited number of enzymes, and the main oxidation states are +5, +4 and to some extent +3. Okay. Now, it is good to know the nature of the vanadium species. The nature of the vanadium species, a kind of a oligomers that is found, are dependent on the concentration of the vanadium and as well as the pH. Most of the times these vanadium species are generally found in their +5 oxidation state as vanadates. Okay. So, this vanadates like phosphates, like silicates, molybdates, you have vanadates also. So, the vanidates are mono, di, tri, tetra up to about deca kind of things are reasonably known. So, concentration of the higher vanidates are generally low. So, if you go for the higher pH, the higher size vanidates are generally little bit more favored. So, the higher the concentration of the vanadate, the higher the sizes of the vanidates are preferred. How do we study? These vanidates are all plus 5 based vanidates. So, therefore, the study is suitable by 51 V NMR, because plus 5 vanadium is what? What is the D configuration? D configuration is 0, D0. There are no electrons in the D system. What is the D configuration of vanadium in plus 4 oxidation state? It is plus 1, because plus 5 oxidation state is 0, therefore, plus 4 oxidation state should be 1. There is 1 electron in D, therefore, it is a nice system for EPR studies. And 0 electrons in D plus 5 is very good for NMR studies. Okay. And what I mentioned to you about vanadates, how these formed, oligo vanadates or polyoxo vanadates. I mentioned their aggregation or their vanadate formation. I would take back the word aggregation, but I would say their vanadate formations. So, aggregated vanadate formations or joined vanadate formations are dependent on not only on the vanadium concentration in the medium in its vanadium plus 5 oxidation state, but also on the pH. Suppose you take a pH as acidic as 3.5. So, the entire thing will be protonated, that is H3VO4, just like H3PO4 phosphoric acid. So, H3VO4, and then you slowly increase the pH to somewhere neutral or a little bit more than neutral, and start increasing the thing, it will become mono negative. Then you make it beyond neutral, it will become di-negative. You go to pH like 12 or above, then it will become tri-negative, because there are only 3 OHs, it can only lose 3 protons. So, therefore, at very highly acidic below 3.5, around 2 to 3, it will be all 3 protons are intact. Above 3.54, one of the proton is lost, so mono anionic. When it is beyond 7 to 8, then 2 protons are lost, there is a dianionic. When it is beyond 12, 13 pH, all the 3 protons are lost. So, it is VO4 3 minus. So, you have a species of this type as a function of pH, as a function of pH. So, you have H3PO4, then H2PO4 minus, HPO4 2 minus, and PO4 3 minus. Not P, in each of this you take it as V, it is a vanadium. Okay. So, it is a vanadium. So, therefore, H3VO4, H2VO4 minus, HVO4 2 minus, VO4 3 minus. It is very similar to the phosphate, that is how I just got into the phosphate part of it. So, but we are in the vanadate. As you go like 2 to 3 pH, up to about up to around 3 pH, around 7.5 to 8 pH, and the pH beyond 8, greater than 8, and then greater than 12. Okay. So, you can see the slide that we have on this. Now, at these concentrations, because you are forming the negatively charged species, so therefore, they can combine. They can combine by the elimination of the water. So, if the two such things are combined, as you can see here, so you can get the H2V2O7. So, one oxygen is less, that means one water is gone, and then you have further 1, 2, 3, 4. So, 4 oxygens are less. So, like that 3 oxygens. So, you have a H2V2O7, and then you have V3 combination, then V4, then the V4 is shown as 1, 2, 3 and 4. Okay. And this is for V5 and for V10. Okay. And these are joined together, the individual vanadate units are joined together through oxo bridge by the elimination of the water. Okay. So, it is basically by two of the VOH groups coming closer, it is like this. You have a with V, one with OH, V with another species. So, of which you leave minus H2O. So, you get VOV, and that is how the links are formed. Therefore, the polyoxovaradates are formed because of that. So, you can see that these are all dependent on the concentration and the pH. As you can see, their different pKa values are there. Now, I talked to you about in the vanadates, mostly these are all vanadium 5, and the vanadium 5 is D0 system, and vanadium 5 which is D0 system can be studied by 51V NMR. Now, here is a very interesting curious plot here. So, have a look at this. This is a vanadium NMR plot. What you have here is a vanadium surrounded by different kinds of ligands. Okay. So, if I take this case, that means there are two oxo kind of ligands, two sulfur kind of ligands. This does not mean 2 O's and 2 S, 2 sulfurs. It is 2 oxo ligands, 2 sulfur ligands. Take here, there are 3 oxo ligands, 1 sulfur ligand. If you take this one, 1 oxo ligand, 3 nitrogen kind of ligands. So, this is what we have. So, therefore, you have vanadium which is surrounded by some all oxygen, some oxygen, some nitrogen, some oxygen, some sulfur, some nitrogen, some sulfur, some oxygen, nitrogen, sulfur. So, that means what? You are changing the coordination sphere. You are changing the ligand nature from oxygen to nitrogen to sulfur. And we know why we are talking about, because I already explained in this particular course several lectures ago, hot, soft, acid base concept, we explained to you. Okay. So, therefore, oxygen, nitrogen, sulfur follows that kind of a thing. Second thing is their electronegativities. Okay. In this case, the what you have on the x axis is a is the chemical shift of not proton, it is vanadium 51 NMR, and on the y axis you have this something called sigma n, chi. So, chi is electronegativity of the atom that is attached to the vanadium, and sigma is summation of all the atoms attached to the vanadium center by the coordination number Cn, coordination number. So, the coordination number here is 4, here is 4, here is 4, etc. Here it is 6, here is it's 6. So, things of that kind. So, you have different kinds of coordination number. So, this is normalized with respect to coordination number, taking the summation of the electronegativities of the surrounding ligating centers to the vanadium. It is very interesting, as you can see. Leaving this one aside, you see that there is a fairly linear kind of a correlation we can draw through this. So, fairly linear correlation you can draw. So, you see on this end you have more of a oxo based ligands, and if you come here, more oxygen is less, nitrogen is more, and oxygen is less, sulfur is more, and nitrogen and sulfur. So, it is absolutely going by the electronegativity kind of a principle. So, the greater the electronegativity of all the surrounding atoms, the more negative is the vanadium chemical shift. The lesser electronegativity around the vanadium, the more positive is the chemical shift of vanadium. And another thing that you need to notice is that you have chemical shifts going from something like -7,800 to +7,800. So, it is a huge range of the chemical shifts. So, this means what are we conveying in terms of the biological vanadium chemistry? Biological vanadium chemistry, if I have a vanadium 5 in some enzyme, in some protein, if I measure its vanadium 51 NMR and try to use this plot, I can get roughly what is the surrounding atoms, what is the surrounding coordination sphere. whether they are all oxygens, oxygens of nitrogens, nitrogen with sulfur, that kind of a coordination, primary coordination details can be obtained. Primary coordination details can be obtained. That is why we are studying this plot. So, this plot has a relevance to the biological vanadium chemistry if the vanadium is in vanadium 5. Now, having looked at that the vanadium plus 5 oxidation state is 0, plus 4 oxidation state is D1, plus 3 oxidation state is D2, etc., let us look at their redox potentials. So, how easily one can reduce, how easily one can oxidize, how difficult one to reduce, how difficult one to oxidize. So, these are the things that we need to understand. So, if you take H2VO4 minus, H2VO4 minus, which is vanadium is obviously 5, just now I talked to you about this, then you add 1 electron to this. When you add 1 electron to this, what will happen? Vanadium 5 will become vanadium 4. So, this is vanadium 4 VO2 plus. This also has a name called vanadile. So, this is generally referred as the species of vanadile in nature. So, VO2 plus is also shown as VO, and this is called vanadile. So, this is vanadium 4 and this is D1 system. So, this is obviously EPR active. So, one can study the EPR spectroscopy, etc. Now, coming to this electrochemical potentials of these, so vanadium 5 reduced to vanadium 4 and the rest of the oxygens going into the water has a very high positive potential, okay, that is 1.31. VO2 plus, this is again a vanadium 5. So, it is a vanadium 5 species. If you add electron, you will get VO2 plus. In this particular situation, this is much, is somewhat little lower, but it is good amount of positive, about 1 volt, and there is 1.3 volt. That difference is because you are doing from a vanadate, which is an anionic species, and here you are doing from VO2 plus, which is a cationic species. That is okay. Now, you take this one and further add 1 electron. Okay. So, you are taking vanadium 4 and then taking an electron, it will become vanadium 3, and this potential redox potential is only plus 0.3. And you take vanadium 3 plus electron is minus, and so that means as you go from 5 to 4 is quite easy because more positive potential. If you put into the formula delta G is minus NFE naught, and the positive value of E naught will become this minus. So, therefore, there is a great minus, that means feasible. 5 to 4 is quite V5 plus to V4 plus is more favored, and V4 plus to V3 plus is somewhat less favored because the potential is plus 0.3. So, this is plus 1, plus 0.3, etc. So, therefore, vanadium 5 to 4 is very easy in the biological systems also, and 4 to 3 is not impossible, but with some difficulty you can make, but going to vanadium 2 from 3 is a negative potential, and that means it is strongly reducing, it will get easily oxidized. That is probably the reason why biological species did not prefer to have vanadium 2 plus, because vanadium 2 plus is a strong reducing agent and its reactivity is also very high. Therefore, the vanadium biological system is very happy with plus 5, plus 4 and plus 3. Now, come to the other redox couples, the oxygen, which I am going to explain when the oxygenase properties, etc., but still we can see right now the oxygen O2, there are 2 bonds are there, that means 4 electrons. So, you can add 4 electrons to this and therefore reduce into the O2 minus kind of thing, that will be 2 protons. So, water 2 of such. So, this is almost equal to reducing oxygen to water. So, the vanadium 5 to 4. Okay. And if you see the vanadium 3 to 2 is as good as the NAD plus, reducing the NAD plus to NADH. So, NAD plus to NADH, so minus point is as much as that, and or 2H plus 2 electron per hydrogen. So, therefore, the vanadium 3 plus 2 plus electron is as much as the NAD plus reduction or proton reduction kind of a thing. So, from this slide what are our conclusions? Our conclusions are that it is rather easy to reduce the vanadium 5 plus to vanadium 4 plus, and somewhat difficult, but not impossible from 4 plus to 3 plus, but 3 plus to 2 plus is going to be extremely difficult, and whatever the 2 plus species, that is product, is going to be highly reactive and strongly reducing agent. Probably that is the reason why it has not preferred the biological systems. Now, let us look at these species being present in the biological systems. These species are being present. As an example, we see that the vanadial species is being found to bind to the transferrin, human serum transferrin, and vanadial is vanadium 4 plus, and I said vanadium 4 plus is D1, and I said this is EPR active. Therefore, one can study this by EPR. In fact, if you take a vanadate and incubate with the protein over a period of time, you would get the Vivo 2 plus, which is bound to, which is vanadial species bound to the protein 2. So, now here we have examples shown over there. This is for the human serum transferrin. So, human serum transferrin, later on I am going to explain when I come to the iron story. This is the iron transferrin protein. It has two lobes, one is called the N-terminal lobe, one is called the C-terminal lobe, and at both the regions you have the iron clusters. Now, this vanadial will bind at both of these clusters, at both of these centers. So, the N-terminal center and C-terminal center. And you know, I explained to you earlier, in the EPR you will get the super hyperfine coupling based on the, for vanadium the I is 7/2. So, how many vanadiums are there in one vanadial? Only one. So, 2 Ni plus 1. So, 2 into 1 into 7/2 plus 1, that is 8 lines. So, what you expect is there are two vanadials, but both the vanadials are not in the same place, they are in two different regions, and because this protein transferrin has got, so transferrin I will be showing later on. So, I will say there is one this lobe and there is another lobe, this is let us say C-terminal lobe and this is the N-terminal lobe. So, it binds at both of these. So, one VO2 plus is bound here, another VO2 plus is bound here, but they are not communicating, they are very far away. So, far away. So, therefore, there is no interaction between them. So, individually you will find. You can see all these things are 1, 2, 3, 4, 5, 6, 7, 8, 9 lines. But this is coming from the different source. So, these are the actual lines coming from the hyperfine splitting lines for these. So, therefore, you can explain all of them very well. Okay. So, the 9 lines coming, these are perpendicular kind of a situation, and each of these, if you see with close by, you have a splitting of each of this peak into two. This one is coming from the C-terminal, other is coming from the N-terminal kind of thing. So, that is that's why one can study these ones too. Here we have shown for a different case, because this kind of a vanadial species is found in biological systems, even in samples of the animal samples or mice samples, and the liver, spleen, kidney, tissue, etc. Kidney, all these tissues, and they can be studied. So, if you study at the room temperature, you find not so very nice spectrum, but if you go to the lower temperature, you will find the spectrum to be very nice and very well resolved kind of thing. Okay. So, therefore, one can study this presence of the vanadium 4 plus species in the biological systems by using the EPR spectroscopy. Okay, let us look at a few other cases where the vanadium is being accumulated. In fact, there is some sea small size animals, sea squirates, tunicates, where vanadium is accumulated, and this vanadium accumulation is found in their body. So, sea squirit's body is 80% of his body is by the vanadium or vanadium based compounds. So, what happens in these things? So, what happens in these things is these tunicates have got some chromophore called tunichrome, okay, and this tunichrome can undergo redox process. As a result of that, it can bring a redox in the vanadium 5. So, therefore, tunichrome reduced going to oxidized will convert the oxidized vanadium to reduced vanadium. So, oxidized vanadium is vanadium 5, reduced vanadium is vanadium 4, and further this is forms vanadium 3. So, you can have some part of the vanadium 5, some of the vanadium 4, some of the vanadium 3, all of these are found in this, and in fact, for the evidence for vanadium of these species have been worked out by small molecular systems as well. Okay. So, this is for the vanadyl vanadium 4 compound, this is for the vanadium 3 compound, these are from synthetic analogues. So, Salin is this kind of a molecule that synthetic analogues you can in fact make 4 and 3 and show this. So, that means in the biological system whatever the vanadate is being taken up from the let us say sea water, because these are sea tunicates, the vanadium 5 is not sitting in the 5, it will go into 4 and 3, and the vanadochrome is somewhat having a structure of this kind. So, what is this one? You have a catechol kind of a groups, and you know that the catechol kind of a groups will undergo very nicely, very easily redox. So, reduced form is catechol or phenol or OH, oxidized form is quinone or semi-quinone, catoquinone, and these are the things. So, oxidized forms and reduced forms can be formed. So, therefore, the vanadium present in these sea animals is in the form of vanadium 4 and 3, though the entry is vanadium 5. They are not entered as vanadium 4, that should be noted. Kindly note that these are the entry point is vanadium 5, not the vanadium 4. In some of the species, there is a low molecular weight compound containing reducing sugar, which is called vanadobin. In fact, the vanadobin also do very similar kind of thing. In this whole figure, what I need is your attention is this is, if you take a central line here, only the above portion. You do not need to so much worry about the portion below. So, vanadium 5 is captured by the vanadobin, and that will convert into vanadium 4, and then this can go into 3, and so vanadium 5, vanadium 4 to vanadium 3, and you have other anions to stabilize some of these. So, therefore, in another system, the previous one was the sea squirit, and this is in some of the cells. So, even in cells, the vanadium 5 that is being taken in cannot be ideally sitting as vanadium 5, it will go into vanadium 4 and vanadium 3. And this goes very well with what we studied for the redox potential. 5 to 4 absolutely very easy, 4 to 3 is somewhat okay, not as easy, but however, with certain reducing agent this is possible, and that is what we are basically finding. Okay, with the vanadate, before we go into vanadium based enzyme, let us look at some effect of vanadate. At this stage, I would like to recall your attention to the sodium potassium ATPase pump. Just in the previous class, I have covered that. And you know what I mentioned there? You have an even conformation of the protein ATPase, the sodium binds, and then this triggers along with the magnesium 2 plus the phosphorylation. So, the phosphorylation will be with the phosphate group, and at that stage protein conformation changes, sodium ions are gone, and this whole thing happens in this particular half of the cycle. And at that stage of the sodiums are lost, the potassiums gain the affinity to bind to the sites in the ATPase, and at this the magnesium activates and then dephosphorylates. So, when it dephosphorylate at that moment, if you have vanadate in the presence, the dephosphorylated protein is replaced by the vanadate, and the second part of the cycle is incomplete. So, thus presence of vanadate will act as a inhibitor for the ATPase activity. So, ATPase is good, this is the half cycle, goes very happily. The second half cycle there is a phosphate dephosphorylation. During that period, if vanadate is present, the vanadium will or vanadate will bind. Once the vanadate binds, then it will not revert back to the normal state, because the vanadate binds at least 30-fold stronger, and also vanadate binds very much stronger to this particular system, and it is irreversible. So, vanadate binding is absolutely irreversible. So, therefore, this cannot be functioning. So, therefore, if in a ATPase cycle, if you add some vanadate, and vanadate and phosphate are very similar in terms of shape, charge, size, etc., very close by, and then vanadate can inhibit the enzyme. So, this is an inhibition of the enzyme. I am not talking about the enzyme activity. Okay. So, the kinds of species that are present are shown over here, the magnesium bound ATP and then vanadate bound. So, with the phosphate, and when the phosphate is gone, vanadate is present. So, the species looks very similar, but the vanadate species is much more stronger by 30-fold, and it is irreversible. Okay. So, in this class what we have studied? We have studied the vanadium can exhibit +5, +4 and +3 in the biological systems. +5 to +4 is quite easy, +4 to +3 is not impossible, though not easy, but it is possible. So, therefore, in the biological systems the vanadium has been found in the form of +5, +4 and +3, and vanadate acts like a inhibitor to the ATPase cycle in the second half, that is the potassium part of the cycle, that is in this part of the half of the cycle. So, we will continue with the enzyme based on the vanadium, which is called vanadium haloperoxidase, in the next class. Thank you very much.